Okay, in this little lecture, we are going to go over chapter 5, which is called a deeper look for instruction set architecture. Firstly, we need to pay attention to the picture here. So for the Manray little computer, this is its instruction set architecture, which means that its assembly language set are all written here. These are all the statements this assembly language set can have. For example, for C++, as a high-level language, we have learned in CS1 and CS2 about all the instructions in C++. You can say integer A, integer B, and integer C, C equal to A plus B. And here, this language set is the assembly language set for Manray, and that is all. All the instruction set are here, including load, store, add, subtract, input, output, halt, and add I means accessing the memory using other ways than we have mentioned. Indirect memory access. Okay, so we have seen the very little instruction set architecture. It is here. It is pretty simple, easy to manage. But we want to talk about in real world. Actually, we can have different design of instruction set architecture. In other words, this was the job done by the CPU designers. Manray is an example about what they have been designed throughout the years for the CPU. What are the true instruction set in the actual CPUs nowadays? Okay, so we are going to discuss the different ways to design the instruction set architecture. The instruction set architecture actually can be different because of the following. Because the following items can be different. The first one is instruction length. Okay, so the Manray has instruction length of 4 hex numbers, which is 16 bits. But definitely, in real architecture that is designed nowadays, the instruction length can be longer. Instead of 16 bits, can be longer. Number of operands. The Manray has 1 number of operands. It was always loading X, load X, add Y, store Z. So the X, Y, Z is the operands. For Manray, it has only 1. But for sure, we can design some instruction set architecture, which is this new language, have more operands. Number of addressable registers. The Manray has 7 registers that can be used. And for real architecture, there can be different registers, and also there can be addressable registers, which means there can be more complex design about registers than the Manray. Okay, memory organization. Well, so when accessing the memory on the Manray, we kind of access one after another, and each of them is 16-bit. But this can also be different. Addressing modes. The example we saw in class used direct memory address, but there can be indirect memory address or indexed memory address. We are going to talk about this too later. So now I believe we have a big picture in our mind. The Manray is just an example. There can be other methods to design the instruction set architecture. Okay, So before giving examples of instruction set architecture, we want to mention this little thing first. It's about the concept of big endian and small endian. If the hex number we want to save in the memory is actually longer like this, then normally we kind of think, just put each of them into the memory from the beginning to the end. So it should be 1, 2, 3, 4, 5, 6, 7, 8 from the lower address to higher address. But in reality, there are two different methods to store them. One is to put as what we thought, the other is to reverse the order, which is to put the last 2 digits here first and the next 2 digits here at the next address, and then until the last one being the first 2 in the address. These 2 are called big endian and little endian. So there are some examples. The values A, B, C, D, 1, 2, 3, 4, if saving in big endian would be like this, but for little endian, it's going to be like this. Okay, but other than how to save the instruction set, we are going to truly start to talk about all other examples, similar to memory but different as instruction set architectures. There are many methods to divide them. For example, saying there is a stack way, there's a cumulator way, general purpose register way, 3 ways, and there are other methods to divide them. It is kind of not good to just memorize the name, but we just have impression it is okay. I think it's more example to see the examples. Okay, so there are a lot of descriptions here, but let's see the examples. Okay. Well, for example, if we want to do calculation of the formula z equal to x multiply y plus w multiply u, there can be many ways of writing this thing out as the assembly language in different instruction set architectures. Okay, so let's see the example. The most direct thing we can think of is, just to say multiply xy, store them in R1, multiply w and u, store them in R2, and then add R1 and R2 to z. This thing can be existing and it is called 3 address arrays because after each of the operation, there are 3 operands. There can also be 2 address arrays, then it would load x to R1, load y to R1, multiply y with R1, load w to R2, multiply u to R2, and then at both, store it back. This kind of architecture is called 2 address instruction set architecture. And both of these are accessing memory randomly. It's kind of whichever element they want, they get x into R1, get y into R, multiply y onto R1, and get w into the R2. Well, the last example here simply come back, which is similar to the memory example. It is 1 address RSA. It's very easy and direct. It is fun to see there is another way to do this, which is a stack ISA. Stack ISA means that the memory is not accessed randomly. Instead, it is accessed by push and pop, which means that we can only do something at the top of the memory. And the language for the assembly language for a stack architecture can be like this. for the stack instruction set architecture, it can be like this. Okay, so until here, we have, what did we talk about? So we have talked about, firstly, Marie is good example, but we can change it by changing the instruction length, changing number of operands, changing of addressable registers, and the memory organization addressing mode. Then we talk a little bit about big endian and little endian. After that, we want to see examples for different other different instruction set architecture. And firstly, we say, there can be many names, for example, stack architecture, accumulated architecture, general purpose register architecture. But then we start to provide examples. These are something really good for let us know more. For example, for a formula like this, it's easy to design such a instruction set architecture, and that is 3 address ISA. Then we can also make it to be 2 address ISA and then 1 address ISA. Then if related with stack, it can be stack ISA. Well, so basically, eventually if you have a research topic, or eventually work for creating assembly language for the CPU, then you must be very good at this. Okay, let's continue. So there are more description discussions, but the interesting thing is here, The PowerPoint is saying that whenever there is an instruction set architecture, Marie kind of have an opcode and then the address. But in reality, there can be 1 opcode and then several addresses. Because you have seen, there are 3 address, 2 address instruction set architecture too. Then we also mention we can also allow the length of the opcode to vary. Then we can create a very rich instruction set. For example, in an instruction set, it is possible the length of the opcode are not the same. And in this way, we can make the instruction set more complex. And the last thing that it was mentioned is that instructions fall into several categories. Data movement, such as the load and store, arithmetic, such as the add and subtract. But there can be more calculation-related instruction sets, such as Boolean bit manipulation, I/O, which is easy to understand, control transfer, and special purpose. Well, so here we just talk about there are so many instruction sets, and normally they do the things like this: move data and calculation. Well, definitely I/O. Okay, that is the little illustration about this lecture. I wish now, based on Marie, we know there can be more complex instruction set architectures with assembly code examples.